Here's your review on Unit 4, which covers bonding. So there were 3 different types of bonding that we learned about. The first one was ionic bonding. An ionic bond is formed whenever one atom gives an electron to another atom. This forms 2 ions which have opposite charges. One positive, that's the cation, and one negative, that's the anion. So in this picture here, we have a sodium atom and we have a chlorine atom. The sodium atom, as you see here, has got 1 valence shell electron. So this outer shell has only got 1 electron in it. If we look on chlorine, we have 1, 2, 3, 4, 5, 6, 7 valence shell electrons. So what's actually going to happen is the sodium is going to give away one of its outermost electrons, the only one it has to give. It's going to give that away to the chlorine. In doing so, in the next lowest energy level, sodium's got 1, 2, 3, 4, 5, 6, 7, 8. So by giving away that outermost electron, sodium actually gets a full outer shell by getting rid of that lone one on the outside. And that 1 sodium electron has been given to chlorine. So now, same story with chlorine. Chlorine also is going to have 1, 2, 3, 4, 5, 6, 7, 8 valence shell electrons. So because sodium gave away an electron, now its charge is positive, and the chlorine gained an electron, so its charge is going to be negative. And those opposite charges attract, and that is what forms the ionic bond. It's the attraction between those ions. The metal, as you can see here in this example, sodium, tends to lose electrons, whereas the nonmetal, in this case chlorine, tends to gain electrons. Or we could involve a polyatomic ion. So more about ionic bonding to make Lewis structures. This is similar to what we did before with the dot structures, except now we're showing the electrons that are involved in the bond. So the first example is sodium chloride. So what we've done here is we've taken those outermost electrons, those valence electrons, and represented them as dots. And I've color-coded here. On your test, you might want to do X's and O's, or if you want, I'll have colored pencils available as well. So the way you do this is you figure out how many valence electrons each of these have. If you look at the table of elements, sodium's in that first column with Roman numeral 1 above it. So that means that it's only got 1 electron represented there in blue. Same thing for chlorine. That's got 7 valence electrons. If you look at column 17, it's got Roman numeral 7 over it. So that tells you there's 7 valence electrons for chlorine. Same story for this next one, except in this case I have sulfur. Sulfur only has 6 valence shell electrons, therefore it needs to get 2 more, and it achieves this by bonding with 2 lithiums. Each lithium has 1 electron represented in blue, whereas sulfur has 6 electrons represented in red. So sulfur needs to take 1 electron from each lithium to have a full octet. Last one here, we have sodium phosphide. So there's 3 sodiums. Each one has 1 electron represented by the blue. And there's phosphorus, which has 5 electrons represented by the red. And again, there's a pattern to this. Whenever you're placing the electrons around the phosphorus, you do 1, 2, 3, 4, 5. So it's top, right, bottom, left, top. And that takes care of those 5 electrons. Same thing over here with the sulfur and with the chlorine. Top, right, bottom, left, top, and right. And that takes care of all 6 of those electrons. So in each case, the atom with fewer electrons, generally the metal, loses its electrons, giving them to the atom with more electrons, generally the nonmetal. Metals tend to lose electrons, and a good way to remember this is the left side loses. Metals are on the left side of the periodic table, whereas nonmetals tend to gain electrons. The resulting ions have opposite charges, so they're going to be attracted to each other. And one key thing that you never want to forget is to show the charges. So sodium lost an electron, so its charge would be positive, whereas chlorine gained an electron, so its charge would be negative. For the next one, it's the same thing. Lithium each lost an electron, so those are positive, whereas sulfur sulfur gained 2 electrons. So in this case, it would be -2. And with the last one, again, all of the sodiums, they lose an electron, so they're +1. And the phosphorus gained 3 electrons, so its charge would be -3. Next bonding type that we learned about is the metallic bonding, which is described by the electron C. So take a look here. Here I have a bunch of metal atoms, and if you look, their outermost energy level, those are all empty. So there's that outermost energy level right there, and it's empty. What has happened is these metal atoms have given up their outer valence shell electrons to something called the electron C. And that's what we see floating around each of these atoms, each of these cations, these little valence electrons. So there's a whole bunch of valence electrons, and now since the metal atoms lost electrons, they become cations. So they're positively charged ions that are sort of floating in this electron sea. So metals are malleable and they conduct electricity and they're shiny. And the electron sea model explains a lot of these properties. So first and foremost, that sea of drifting valence electrons insulates each of the metal cations from touching one another. So by preventing them from touching each other, if I were to smack the metal with a hammer or subject it to some kind of pressure, those metal cations can easily slide past each other. And that's because those valence electrons that are in the electron sea kind of act as grease that prevent those cations from ever touching one another. In an ionic solid, whenever I smash it with a hammer, I force like charges together. And we know that opposites attract and like charges repel. So if I force those charges together, it'll actually cause that solid to shatter. But in the case of a metal, we've got those electron C that prevents those cations, those positive charges, from ever touching each other. Lastly, electricity is just a stream of moving electrons, and metals are already set up for this. The electrons are already freely moving through the metal, so it's very easy for them to conduct electricity. And the last type of bonding that we learned about was covalent bonding. Covalent bonding involves two nonmetals that share electrons. Neither one is willing to give up an electron or to receive one. So this is where we have electrons being shared. And as a result, depending on how many electrons are being shared, we could have single covalent bonds, we could have double or triple covalent bonds as well. This also involves polarity. So only covalent bonds can show polarity. So in a polar bond, that's where electrons are shared unevenly. That's kind of like one atom is more electronegative and it hogs all of the electrons. So the electrons spend more time around that more electronegative atom, causing sort of a disparity of charge at the two ends of the atom. And of course, nonpolar is where the electrons are shared unevenly. Now, one of the most challenging aspects of covalent bonding is drawing the dot structures. So here are some steps to help you kind of get to the Lewis dot structure. First thing that we want to do is figure out for a given atom how many electrons we have. And let me remind you that you do this by looking at the table of elements. So you can look and see based on the position, which column each atom is in, to figure out how many valence shell electrons. You can also always do an electron configuration and count the electrons. Then you have to figure out how many electrons you need. Pretty much every atom is going to want to have a total of 8 electrons to make an octet. A big exception to that would be hydrogen. Hydrogen only needs 2 because it's only got a 1s orbital, so that only needs 2 electrons in order to be filled. And we take those two pieces together to figure out the number of bonds. Then we got to figure out what the central atom is. So the central atom, 2 rules. One, it's never hydrogen. Hydrogen can only form 1 bond, so it doesn't make sense for that to be in the center anyway. And then it's going to be, if it comes down to 2 other atoms, it's going to be the one with the least valence, number of valence electrons. Then we assemble all that information together into the bond skeleton, and then we make the Lewis structure. No, you do not have to show each of these steps on the test. If you're able to just look at an atom and go, then that's fine. But these are just steps to get you there. So let's do an example. First one that we're going to do is HCl. Okay, HCl is hydrochloric acid. So first thing we got to figure out is the number of electrons that we have. So we've got 2 different atoms here. We've got hydrogen and we've got chlorine. So hydrogen is in that first column. It's only got 1 valence electron. And chlorine is in the 17th column, so it's got 7. So the total here between these two is 8. Now we got to figure out how much each of these atoms would want. So total, hydrogen is going to want 2. Remember, everything wants 8 except hydrogen that wants 2. And chlorine is going to want a total of 8. So if I add these together, I get 10. Next up, we got to figure out the number of bonds. So what we're going to do is we're going to take what we got in the second step and subtract the first step. So that tells me how many electrons we're short. So the second step, we got 10. Subtract 8, and that gives us 2. So this is how many electrons we're short from having the ideal number that we want. We're then going to take this and divide by 2. Now the reason we're dividing by 2 is because there's 2 electrons per bond. So if we divide by the number of electrons per bond, what we're left with is the number of bonds. So we got 1 bond. Okay, next question is about what the central atom is. Now remember, it's never going to be hydrogen, and it's going to be whatever's left that has the most number of valence electrons. In this case, we've got hydrochloric acid. It's just H and Cl. There's only 2 atoms there. So neither of them is really in the center. So this isn't really one where this step applies to. Okay. Now we're going to assemble everything that we know from all of the previous steps to make our bond skeleton. So I know that I have a hydrogen. And I know that I have a Cl. And I learned up here that they're connected by 1 bond. So that's our bond skeleton. Alright, next up I got to translate this bond skeleton into a Lewis dot structure. So this is another time whenever I like to color code. So first thing I'm going to do, I'm going to draw my chlorine. And my chlorine has got 1, 2, 3, 4, 5, 6, 7 valence electrons. So the only thing that's left now, I got to fill in my hydrogen. And hydrogen only has 1 valence electron. So there you are. Now I didn't count to put the electrons around hydrogen, top right, bottom left. I didn't really have to do that because all I'm doing is I'm taking those other atoms and using them to fill in any holes. And there was only 1 hole for chlorine. So now that I put all that together, I now have my Lewis dot structure for hydrochloric acid. Alright, so let's do another example. Why don't we go ahead and do uh, phosphorus trihydride. Okay, so first thing to do is to figure out the number of electrons that I have. So phosphorus is going to have 5 valence electrons, and hydrogen is going to have 1. But there's 3 of them. So that's 8 total. Now we got to figure out how many we need. So phosphorus wants to have a total of 8, and hydrogen wants to have a total of 2. But there's 3 hydrogens. So that gives us a total of 6. So if I add these guys up, 8 and 6 make 14. Now I got to figure out the number of bonds. So I take what I got in my second step, 14, subtract what I got up in my first step, which was 8. Difference there is 6. So that's how many electrons I'm short. And I divide that by 2 because there's 2 electrons per bond. And this gives me 3 bonds. So this is one of those where there is going to be a central atom. I've got 2 options. It's either going to be phosphorus or it's going to be hydrogen. Okay, we have 2 rules. First rule, it's never going to be hydrogen. So the only thing I'm left with is phosphorus. If this came down to, say, let's say you had 2 choices, you had carbon or oxygen, it's going to be whichever one has the least valence. So in that case, it would be carbon. So now I got to draw a bond skeleton. So I'm taking what I know so far. I know that I've got a phosphorus in the middle, and I've got 3 hydrogens. And I'm going to need this to be connected with a total of 3 bonds. So if I use 1 bond on each, 1, 2, 3, there we go. That's our bond skeleton. Just now I got to take this and just put it into a Lewis structure. So again, I'm going to count on my pattern. 1, 2, 3, 4, 5. So that's how many valence electrons phosphorus has. And we can go ahead, we can fill in the hydrogen. So each of these guys here has a blank, and that's where we're going to put a hydrogen. So I'm going to represent those with X's. So that would be the Lewis dot structure for this particular molecule. Now the next step would be to take this and to figure out what its shape would be in 3 dimensions. That's the Vesper shape. The way you do that, you got to look at the number of atoms as well as the number of lone pairs. So, for example, we've got 3 atoms attached to the central atom, and we've got 1 lone pair. So, Vesper theory is about how these atoms and electron lone pairs are going to arrange themselves in 3 dimensions so that they are as far apart from one of each other as they possibly can be. So in order for that to work for this type of molecule, it's going to have to be trigonal pyramidal is what's their shape going to be. So you look at that sheet where it's got all the different shapes on it, and you can see that the different shapes correspond to a different number of atoms and a different number of lone pairs. So that's just a sheet that you reference. To figure out the polarity of this type of molecule, we're going to take a look at its shape here. So you could look up electronegativity values and subtract it and figure out what direction the polarity is in, but it's just going to be easiest to take a look at the atom. If you can split it in half and it's different on the two halves, which is another way of saying that it's asymmetrical. If it's asymmetrical, then you know it's polar. So if I split this in half this way, it's pretty much this table on both sides. I got a hydrogen here, half a hydrogen on each side, and then my lone pair, everything's split down the middle. But if I do it this way, I've got a hydrogen down here and no hydrogen up here. So I know that this must be polar because it's asymmetrical. Alright, so this is a lab that we did as a virtual lab, and it shows the different properties of the bonding types. So first one is ionic. Key features about the ionic bond. It's got high melting and boiling points, and it does not conduct electricity unless you add it to water. So right away, if you see something that has high melting and boiling point but doesn't conduct, you know right away that that's going to be ionic. Next up is metallic. So think about what you know about metals. You know that they melt at high melting and boiling points, and you know that they conduct electricity. So anytime that you see these two features, you know right away that it's going to be metallic. It's also the only one that conducts electricity in its normal state. So ionic compounds conduct electricity, but only when added to water or melted. So last up are the covalents. Those are going to have low melting and boiling points, and they do not conduct electricity. So there's polar and nonpolar. And how do you tell the difference? Well, that's this section in purple here. The solubility is going to determine if it's polar or nonpolar. Remember, like dissolves like. So polar is only going to dissolve in a polar substance. Nonpolar is only going to dissolve in a nonpolar substance. So that's how you tell the difference. So the table here, this is stuff that you need to know and have committed to memory. The way you would use this is if I had some unknown substance, substance A, and if I were to find out that it did not conduct electricity and it had a high melting and boiling point, then I would know that substance A must be ionic. So that's the way that you'll use this table. Alright, so that covers Unit 4. Here's some key ideas to keep in mind. You need to know the bond types well. Again, ionic, metallic, and covalent. For example, something to be polar or nonpolar, it's going to have to be a covalent bond. Ionic bonds always involve charges, and metallic bonds always involve metals. Remember, like dissolves like, so polar will only dissolve in polar, and nonpolar will only dissolve in nonpolar. And you should know how to find the shape of molecules given only the formula. So if I gave you just a formula like this, alright, you're going to have to look at that formula and figure out quickly what shape that would have in 3 dimensions. So a quick Lewis structure, and then counting up the number of atoms and the lone pairs to figure out the VSEPR shape as well. And again, you should also be able to check for the polarity. So once you draw this out, you should be able to tell, oh, well, this is going to be this is going to be polar because it's asymmetric. Another thing to remember is that 2 points make a line. So in the example of hydrochloric acid, there's just 2 atoms here. The only thing that this could possibly be is linear. And again, this one would also be polar because if I cut it down the middle here, it's different on the both sides. So that's your review for Unit 4.